Alright, welcome back for another episode, or video, or whatever you want to call it. So, I'm assuming by this point, if you're watching this video, you have seen the two videos on types and kinds, which is really just types part 2, and hopefully as well the video on Hangman, just to see a kind of quick example, not really quick, but a simple example, a simple, hopefully well-explained example of how to code in Haskell. Just going to get my timer going. So now, and I say that because you could argue in a way this is kind of getting advanced. It's not really, because it's still pretty simple, but it is starting to get into more theory that is away from immediately how to write a function. Because what we're doing here is we are learning how to effectively overload. And so overloading in object-oriented languages, you would have classes as well, but a very different type of class. And so these classes, I'm not an expert by any means on, object-oriented programming, but if I recall correctly, you are writing a class that defines how to create an object, and it has a certain number of attached functions about how to work with that object. Here, we are writing a type class for a given data type, and that allows us to write functions which are overloaded. So what is an example of an overloaded function? Let's get into it. The easiest, quickest example of an overloaded function is show. So we have the show type class here. So I just copy and pasted this from, what was it again? Just from Prelude. But you could easily find out about this by saying info show, except if I do import Prelude, into my terminal, and then I ask info on show. So you guys have seen :K, :T, and now :I, which is just info. And we get this massive thing here. So there's a lot of instances of show, probably the most instances of any type class. And the reason for that is what show does is it turns some type, which it has a definition for, into a string. So that's very important how I've worded it, very intentional. It's very obvious, like show cannot, the Haskell compiler cannot read minds. It's not just going to figure out how to do show for any given class. And that may be obvious, but I think it's just a point worth highlighting. Any class works for any instance it has. And so, for example, we would have an instance for show character, and that's kind of a funny one. Instance for show int, and it would say how to turn an int into a string. And so very simply, it would be a lot of mappings like 1, 2, 1, and that would be what show is. We can even see this if we do exactly what we just said. And so, of course, we could have a function like our puzzle type in the Hangman game, where we could have a show instance for it. I believe, do I still have puzzle? No, this is a different project. But now we could write a show instance for my type. I kind of made a little joke here with my type, get it, haha. And so I guess I have a couple types, or instances of what my type is, and so so what else? I just want to make sure I don't miss any theory here. So yeah, well, I guess the last thing I'll say in terms of theory is that I am excluding numbers in math and all of that from this lesson. I will talk about them in the next lesson. I believe it's the next lesson. And I will only be going over EQ, show, ord, enum, and read, because those are the most simple basic classes that you would use no matter what what library you're using. Other than these classes, every library, most libraries will have at least sort of one class of their own, which overloads how to deal with different types in that library. Now, so let's get to it with show. So this is what a class declaration looks like. This is the syntax of it. So we have here, this is where we'll start with, where we look with our eyes. It's saying minimal is either shows prec or show. This bar denoting or. We might also have something like this where it's like some other function, meaning we either need to define, in this case we would either need to define shows prec or show and f, but here we just need to define show. And so this is really simple for my type. And I guess I'm kind of jumping ahead a little bit. Everything else here, therefore, we don't really need to think about. This is the copy and pasted definition, excluding some comments that I took out as well. And effectively, when you see this minimal and there is other functions, it's either they are defined wholly in the type class itself, and it doesn't really matter, what the input is, as long as it has some sort of information about how to use show. So, for example, we could see that shows prec here is using show in order to write its own definition. Same with show list. Shows is actually a function which I have not copied and pasted, but is from the original library. But the point is, as long as it has minimal show, it is able to figure out the rest of the functions. And we could have plenty of functions here, and it would still figure them out. Now, when we write an instance in Haskell, this is a simpler instance, and perhaps I should show ord as well, come to think of it. But instance show of my type, where, and now this is where we're actually defining how show would work for my type, and this will give us the as long as we can write this in a way that doesn't, that actually works, then we have an instance of show for my type. So if we have show Rihanna, we're going to do something very complicated here, and we're going to say Rihanna, and we have just converted it. Same with Taylor Swift, beautiful woman. We are also just going to type it out like this, and then we have an instance of show for my type. Let's see, does this actually compile? Got to. Maybe that would be not easier. Cool. So this means that this compiles, and this is a valid instance of show for my type. Probably could have told you that before we saw it compile, but now you guys believe me. So aside from that, we also have EQ. So EQ is again the same thing. Well, it's pretty self-explanatory. We could say EQ for my type, and what we would have here is just simply that. Well, I forget what. I think we just need to define how equals works, and actually, I can figure this out by just looking at EQ. So we see that it has two functions here, two core functions in the type or the class definition itself, and these are equals to one another. So A is equal to this A, and it will give us a bool based on that, and then not equals. So obviously does look different from other languages where they have the built-in syntax of equality or non-equality. But what's interesting here is that we have effectively with now talking about class declarations, we've seen how imports just by virtue of doing whatever, and data declarations and function definitions. Aside from one last thing here, we have covered all of the actual core Haskell syntax. And so when I say that, this is not syntax here. I could create my own EQ class where I say that instead of this equal sign, it's just the literal word equals, if I so wanted. And I guess, there is other parts of little tiny pieces of not as important syntax that we don't actually need. They're more just there for helping us out. But we could literally pretend they never exist, continue on, and be good. We've effectively covered all of the core syntax. And it was quite simple. It's really just a couple keywords and how a function looks and how an instant declaration works. So now, so if I was to create EQ for my type, it would really be simple and just saying Rihanna equals Rihanna, true. If Rihanna equals Taylor Swift, not true. The ORD of, so I guess then this gets us into ORD. So I actually had thought that enum was a superclass of ORD, but I guess that's not true. One more piece of syntax here is, actually this kind of nicely leads into that last bit of syntax. I've just been lazy and said stuff instead of actually doing the copying over, this stuff here. So let's just check that out. So ORD. You can see ORD has a lot more functions. It has compare, which returns an ordering, which is, you don't really need to think about it. You can look into it. It's really simple, but not worth the time here. Less than or equal than, etc., max, min, and in this case, it's just comparing between the two. So if it was like max of 1 and 3, it will give you back 3. Vice versa for min. But anyways, so this last little bit here, this arrow, is this kind of sideways house. Just for the fun of it, is the last little bit of syntax. And so we see this here, as well as if we had a function like this, that is where we'd also see it. So what this means is that our function f can take any type A so long as that type A has an instance of show, and it will do some sort of, it will return an IO tuple, or do some IO action returning a tuple. Same with here, we can create any instance of the class ORD for A as long as that A already has an instance of EQ. So this makes sense when we think about it, and it might not make sense with how I explained that right there, but it makes sense because what ORD is just ordering, right? What comes first, if we thought through 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, everyone could tell me what comes first, what's the lowest, what's the highest, in what order they go in. That said, how do we actually do that? And I mean, implicitly what we're doing is an equality check. So we're seeing is 1 equal to 2? No. 2 is greater than 1. And so we are ordering in that way. And that's why we, without even looking at the actual definition of ORed, I guess we have it here, but without even looking at the actual definition of ORed, we can just logically think through why this constraint here makes sense. And now, same with this guy here. This makes sense for something like, this is an actual type signature here for print. So we used put string line for our hangman game. And so put string line, it's type. I'm just going to do that. Put string line was of the type string to IO. So it only worked with a string. And so really, print is just a fancier put string line. Because what it's doing is it's taking any show instance and turning it into A and then doing IO with it. So there's no magic going on. We could do this we could print almost any type, we could print any type. I should say we can print any type that has a show instance, and that is a lot of them. Not every single type in Haskell has a show instance. For instance, no pun intended, but maybe slightly, we cannot print functions. Functions do not work to print. So let's go and do this. If we print true, I'm just gonna, so annoying. I already did that. If we print prelude.true, this is just because I still have the other module there that I have to do prelude. This is how you refer to a type in a specific module, because we have two definitions conflicting here, but whatever, not really important or related to this lesson. But we can see that it is able to print true, and this is only because if we look at the info for prelude.true, we can see we cannot. Well, I guess we'd have to look at the prelude.show. And we could find somewhere in here. Where is it? Somewhere in here. Oh, there we are. Prelude.bool. And so that's why we are able to do that. And I want to make that very, very clear because, if you think there's magic going on, then that's not really going to help for, actually developing and running into problems where you're confused. Every class just has a given instance for some number of types, and will allow you to use the functions, the methods of that type class on that type, which has an instance, in order to do some stuff. So, for example, if my type had EQ, ORed, enum, read, show, I could do these ones here. I could do any of the functions that are given by these type classes. And I guess the last one I didn't really talk about, and it's not really an important one. I don't recommend it either, except for if you are very conscious of it, because it's very easy to fail. If I was to say read 1 is an int. Oh, what am I doing here? There we go. So this can turn. So what the type of read is it can take a string and convert it to anything that or to a specific thing that has a read instance. I don't believe this would have worked if I didn't specify int. Yes, it would not know how to look for or what to look for. But also too, I do not recommend it because I believe what happens if that's something that you could avoid with real parsing. It's just a really simple parser. So enum as well. Enum, if we look at the info for it, so really what this is sorry, let me try to do a quick example. No, I think I forget how to do this. Oh yeah. So this is very similar to ord, and it's kind of like enumerate in Python. I could do enum from 2, which is really the only super useful function here, in my opinion, unless there is a better way. So I can enumerate from 1 to 10. That's that. And I think that's really it. We talked about superclasses with our ord here, which is ord being a superclass of EQ. We talked about the syntax. And then there's one last thing. So I'm really lazy, as I've mentioned a million times before. So I really do not want to write my show instance. That would be just too much work. I do not want to do that. I also don't want to write a show instance or an EQ instance or an enum instance or an ord or whatever. So for these basic type classes and for these basic type classes, I will say that you can just do this keyword here of deriving. So you can do EQ, show, ord, enum, read. What else was it? EQ, show, ord, enum, and read. Oh, perfect. And this will compile as soon as I get rid of my crap. Just gonna do this. Not easier. There we go. So this compiles and will give us an equality between Rihanna and Taylor Swift. So they are not equal. I'll let you guys decide. Well, actually, no. The last thing I need to say about ord that's kind of interesting here is I find it interesting how ord derives itself, and that is just from reading from left to right. So if I recall, Rihanna should be greater than Taylor Swift. They are both beautiful women, but, you know. Oh, wait a minute. Does it make sense? So is this? Oh. Well, Taylor Swift. Interesting. You know what? I'm going to do a quick experiment here. Who else? One that comes to mind quick. Alright. What about Megan Fox? Interesting. So I guess it was the other way around of what I was thinking. Haven't really needed to use that in a while, but cool. So yeah, I guess what I should have said is that the you know what? Yes, that makes sense. I was saying this wrong because it would be like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So with ord being derived everything from the right, there's the right most value in terms of your definition, or the last value, I should say, to be more general, is going to be the highest value. And for that point, I don't think it's a good idea to derive every single type class. Something like show, you always want to derive show, just because even with complicated types, it's helpful for debugging. But use it wisely. And that's definitely all that there is to say about type classes. I hope you enjoyed, and have a good morning, noon, afternoon, night, whatever the heck the time you're watching this is at. And good for you for learning Haskell. You rock. See you next time. Please like, share, subscribe, all that good stuff. Blah 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 blah. And bon voyage.